Hi friends, welcome to follow up. Let's have a look at problem 938, range sum of BST. So here BST is binary search tree. This problem is today's daily challenge. So we are going to look at some solution formats based on traversals, but the key point is to use the binary search property in this problem. So first, I'm going to digest the requirements of the problem, and then we do the coding. So as the problem's logic is rather straightforward, I guess we will focus on the coding formats for this problem. So now let's look at the problem requirement. So here we are given the root of a binary search tree with two integers, low and high. We want to return the sum values of all nodes with a value in the inclusive range from low to high, both inclusive. So you can understand this one as a closed interval. So here we have several examples. In the first example, the range is 7 and 15, right? So you can see this one is inbound, this one is inbound, and this one is inbound. So totally we have 7 plus 10 plus 12, that is 32. So if you look at example 2, the low is 6 and the high is 10, right? So in this case, because the root value is 10, if you look at the red subtree, it's going to have values greater than this 10. So we don't need to look at this one. So we look at the subtree rooted at 5, right? So we look at the values. But you know, 5 is less than the lower bound 6. So the left subtree is even smaller. So we just need to look at the tree rooted at 7. So here we have 7 and we have 6. So we're going to, here in between we forgot this 10, right? We need to include that. So here we have 6, 10, 6, 7, and 10. So in total we get 23. So that's the problem, the two examples. They're very simple, right? So here the main constraint is the number of nodes is given by this range. So it's not empty, and the number of nodes is bounded above by 2 times 10 to the power 4, right? The node value is in between this range, and the low and the high also in this range, and node values are unique. So with that said, we are ready to do the coding. So before we do the coding, let me give you the binary search tree property. So basically it says that the root value is greater than the left subtree or left child value. Let's see, left child or subtree value, and the root value will be strictly smaller than the right subtree or right child or subtree value. So here I write this subtree, so you can regard the red child as a red subtree rooted as the red child, right? So in other words, this is recursively holds, right? So this is the binary search tree property. So now first we are going to give a solution based on recursion, but we can just do a plain traversal, right? So this is very simple. First we're going to use plain traversal. So this is nothing special. Let's write in a recursive format. If not root, so in other words, it's an empty tree. So here, though the tree given is not empty, but we want to use this one as a base case. So in this case, we are going to return 0. And otherwise, so let's see, if low is bounded, is the root value is in between this bound, let's see, then we are going to do the return for this root value plus self range sum. So we're going to do the traversal for the left subtree, that is root left. So we don't care if it's empty or not, because if it's empty, it reduces to the base case, it's low and high. And then we are going to add the traversal result for the right subtree, root right, and the bound is the same, low and high. This is the case. One other case is the root value is outside this bound, right? So we just need to copy this one, but we do not include the root value. Right. So this will serve as a solution. Let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So now let's see here why we write plain traversal, because we didn't use the binary search property, right? Or we didn't use the structure. So now let me copy this version and let's do a to another solution format. So here I'm going to mark this one as version v1. So here we have low. Let's use say left, right. So we change this just for some convenience. So first we see if not root. So we still use this one as a base case. So now we are going to consider the relative smallness or largeness of the root value with respect to the bound, right? So if r is less than the root value, right, then we cannot go to the right subtree, because the right subtree contains values larger than the root value, right? It's even larger than r. It will, all the nodes will have values auto bound. So we just need to look at the left subtree. So we're going to return self range sum. So root left. So the bound will be the same, L and R. So this is one case. Another case is the left lower bound is greater than root value. So in this case, we don't need to look at the left subtree, because left subtree has values smaller than the root values, right? So in this case, it will be all smaller than the capital L. So in this case, we just need to look at the right subtree. So root right, so L and R. Otherwise, so we are going to look at both. So in this case, we are going to return self, so root left, L, R, and then actually we need to have this root value. And then we do self range sum, root right, then left and right, right? So this way of writing, so actually we specifically used still recursion, but we used the binary search tree property. So now let's do a test. It passes one example. Now let's look at the generic case. Yeah, it passes all the cases. Yeah, I guess so. Here for this problem, we wrote two formats of solutions based on recursion. Actually, so if you want to practice or just for pedagogical purpose, you can also try to write the solutions with in iterative format. That's actually a good exercise you can try. So with that said, I guess that's it for this video. Thank you.